shifting everything up 3. I know this point right here is now up here. If it's vertically shifted up 3. Someone give me an idea, and then we'll get the graph. Something else is being shifted up 3 that sometimes we overlook. Why do you think it's being shifted up 3? It's obvious, but you sometimes will overlook it. That'll help me quite much. So when see anything else that I should be aware of is as I start shifting everything up 3. Yes?
There's going to be an x-intercept?
Come again.
There's going to be an x-intercept?
There might be an x-intercept. We'll find out that shortly. I bet there is. But in terms of shifting, though, I've got this point right here now shifted up to 2.
That's why.
Is this axis. You see this x-axis? As I start shifting, sometimes we'll overlook it. It's also being shifted up 3. So this axis, this horizontal asymptote, is now up here 3. So it's now, in blue here, up here at 3. Mark, that's not gonna work for me, I guess. We put it in black here, guys, and I'll find a blue marker here to finish this out. And then let me make it look like this so you guys can see it. There's my x-axis shifted up 3. So this horizontal asymptote is now up here. Oh, wow, okay. Now, is that enough, do you think, to get a shape of this red graph all together being shifted up 3? What do you think that final result will look like as that red graph is being vertically shifted up 3? Any ideas? Cross, oh, you want to pick this up right here?
Yes.
Perfect. Now, describe the shape. What do you think the shape will look like when I take this red graph and take it up that way?
Same as red one, never touch it.
Okay, here we go. I heard that. Are you telling me it's going to look something like this?
Yes.
That's my red graph vertically shifted up 3. With that boundary up there, of that horizontal asymptote there, now we guys, this represents, if we have no mistake, this represents the final graph of this. Done. Yeah.
Just asking, where's the defined, A must be greater than 0? What's that?
Beautiful, beautiful. Now, wait, Professor, there's a restriction on what, the A in this case? And I know what you're looking at. I know exactly what you're looking at. You're saying there's a negative sign right here, Professor, right? And does that sort of messes up in terms of that definition? Because the definition for the base was what? A must be greater than 0. Guys, guess what's acting as the base of this? Guess what's acting as the base of this? You see the 2 there? The 2 is going to be the base. If they wanted -2, which they can't do, but if they wanted -2, they would have done like this. As they said, did not enclose that. They're saying, no, the base is merely that. That's my base. That's the A that we talked about earlier. And if I do it like that now, that satisfies the condition that A must be what? Greater than 0. That satisfied? Okay, so they should do that. So we're okay then. All right, guys, the graph is done. Oh boy. Can anyone give me the domain of that final blue graph? What is this domain from left to right? Based on the way the graph looks. The domain is from left to right is what? Any ideas? It goes out this way and it goes out that way. What might you say the domain is? Is it all real numbers? Now the range The up and down, be careful. How would you describe the up and down? Because I see the blue graph is dropping down forever. So I know that's negative infinity. How high up does it go? Toward 3. Will it ever reach 3? No. There's my range. Domain, range, there's the graph, and we did through transformations. Guys, take a close look at it, because Lorena, I think you're telling me maybe there's something else there to mention in section 4.3 before I leave it, right? Is there something else? Okay. We'll look at it. Yes?
Would you ever need to find the x-intercept?
Beautiful. That's exactly. In fact, I had a student, concerned about the x-intercept before I even started here. Now you say, Professor, hold on, because this is what will be in this next section. She's telling me, wait, Professor, it crosses the x-axis. Can we find where it is precisely? In other words, she wants me to find this. Beautiful question. That means go back to my original function and set it equal to 0. Look at this, guys. That's where you find the x-intercept. You said y is equal to 0. Now you got to solve for x. Look at this issue. Move the 3 over. Well, we'll see how much of an issue it might be. Got that. Then you might what? Want to multiply or divide by negative, make it look a little better. This now becomes this, which is much better to deal with. And now you've got to solve for x. Does anyone in class at this moment, I'm so glad she asked about this. Does anyone think they know how to solve for x on that? And before you give me an answer, if it looked like this, on the side, if it looked like this, everyone in class would say, Professor, the answer is 4. 2 to the 4th is 16. If it looked like this, quickly say, what? It's 2. 5 squared. That's easily done here. Does anyone have an idea of where we're going? Where we're going? We're moving to that next section called what? Logarithms, to come up with what that x-intercept is. We cannot finish this up. Look how strange that is. Until I introduce logs. And then I'll come back to this and find the x-intercept. Well, I see where it is. It's over here somewhere. Looks like it's going to be a negative number. I can't find it yet. Okay, glad she asked. Now, Arena, what else did they discuss there, or did I discuss there? So-
Natural exponential function.
The natural exponential function. Did I mention E?
Yeah.
Okay, Mr. Park, get ready. Mr. Park and I quickly discussed after you guys were taking a break, as you guys were taking a break. She says, Professor, now they want you to go into what they call a natural exponential function. In other words, the base here is not 2, it's not 3, it's not 4. It's going to be a positive number by restriction. It's not one of those. It's a number recognized in mathematics and labeled as E. And I've heard different stories why mathematicians chose E to represent this number. I've heard this came from the Swiss mathematician who spelled his name this way, Euler, and it started with an E. And they recognized that mathematician and used small letter E to represent this number. But what is it? Mr. Park. And this is where Mr. Park's gonna help me out. Guys, on the side here, and I'll come back to Arena's concern there. I'm going to take a look at something a little strange here. A table, you have an X column, and then on the Y column, something really strange. Looks like that. Now I'm going somewhere with this, so just bear with me. I don't think anyone in class has ever seen 1 plus 1 over X all raised to the X. I don't think. And in the X column, I'm going to place at random these numbers. I think I'll jump up to a million. Now, right now at this point, point, I'm trying to find the limit as that x gets large. X is approaching infinity. X has been a large number. What effect does it have on this expression over here? That's what Mr. Park and I are going to look at. Guys, if I start with 10 in that strange expression, I'm going somewhere with this, just bear with me. It looks like this. Or, since he's going to use a graphing device of some sort, a calculator, it might be wise to put it as 1.1. Mr. Park, see what 1.1 raised to the 10th gives me.
It's 2.59.
How much? 2.59.
2.59. 37.
Now, ask for more digits later on. If I try 100, larger, in that strange expression, it looks like this. And it might be wise, since you're going to be using a calculator, to think of it like this. See what that's close to.
2.7048.
2.7048. Now, guys, bear with us. We know where we're going. Now, go up to 1,000 in this strange expression. And if you're doing this on your own, or he's doing it, it might be wise to do it like that. Raised to 1,000 of all things. What's that close to?
2.7169.
169?
Yeah, 169.
Like that. Okay. Let's try 10,000.
We get
Oh, hang on. Try to write this down, then you'll get. Tell me what you get.
2.7181.
That 181?
Yeah.
Okay. Let's try 100,000. I'm just going to put that down real quick and you understand what it is. Let me show my students, though, these large numbers are taking me somewhere.
It's 2.7182.
Wait. So this one's 2.7182. Try million.
Million? Okay.
1 million. What's that close to?
2.7183.
Sure. You sure you did this correctly? I mean, let's say to 3 decimals. You get to 4 decimals. Are you telling me back up here, you sure? You got that, right? And down here, I know I've got a 4th place there, but that to 3 decimals. And that to 3 decimals. You got those? What? Now I can do 1 million, I can do 10 million, 100 million, and guess what? It stays close to 2.718. And with that demonstration, this is the approximation for this letter or number, E. E is close to 2.718. Based on what you see over here. With that said, though, all we are concerned about is, shortly here, this. Hang on just 1 second. And I'll ask for Rena, if there's anything else there. Okay. Now, guys, can anyone tell me, this is E, roughly 2.718. Is E equal to, I'm going to show a little calculus here, limit as x is approaching infinity, and by the way, does my table show x getting larger? Is x getting larger and larger? X is approaching infinity. Of this expression, we accept as E. That's what we discovered to help the table. Now this is calc notation. Looks strange if I were a beginning student in my math and I'm going to pre-calc before I go to a math 7. I'll say, what, professor? That's E. And its approximation is 2.718. Now, what do they want us to do to close this down? They say now, since you sort of know what E is, roughly 2.718, and what strange thing happened here to make it happen, they want us to now move into part 2. In fact, I've got that out of the way. Part B. Part B, and Arena, tell me what were they asked me to sketch here?
F of x equals e in front of x.
Yeah, now take E and raise it to the X. Now, can I consider that to be an exponential function with the E? And I think the restriction on the base is what? It has to be greater than 0. Is E, have we determined that E is greater than 0? Yeah, it's 2.718. If you want to use E as a base, go for it. Now, what does its graph look like? I'm going to do it quickly. If you move to Math 7, Math 8, and they say, do a quick sketch of what E raised to the X looks like, graph. And you can use some values here. But I'll accept, for the purpose of what we're going to be doing, is that Professor, will its shape, E raised to the X, they call it the natural exponential function. Well, it looks something like, before the break, this graph. Put it in red here. Well, it looks something like that. E raised to the X, I think I used 2 raised to the X before the break. It's going to sort of resemble that. It will. Guys, the y-intercept on this is what, 1? Right here. Now, I think the y-intercept on the 2 raised to the X I did earlier was 1. So if I'll accept that as, without you going through a table and plotting points and seeing what the shape looks like, it's going to look something like this. Let's call this y is equal to E raised to the X. And domain range is easily seen. And that's its shape. That's all I want to say about E raised to the X. Professor, how does it look? Its graph looks like this. Where did it come from, Professor? It came from this business, which translates into this statement. Okay, guys, any concerns at this point? Rena, before we get overwhelmed with all this. Does that take me now into the next section or not? It does. Okay, now, is the next section logarithms? Okay, I gotta slow down. Here we go. This is all part 1, these were exponentials. There's that E in there. Hey guys, I'm way over here. You can't see, let me know. She says, Professor, to close down, all you gave us, we're going to start doing something with a word called logarithms. Let me use the abbreviation here. Log. Just abbreviate log. Now, before I jump in, let me give you a little description of what's going to happen, a few examples, and we'll go from there. Guys, I want you to associate with the word logarithm, or the abbreviation log. Associate this word. Excellent. Now, so Professor, what are you going to do now before we jump into some work here? Arena, check and see if I placed anything on there in terms of examples, or did I not?
Yes.
I did. Like what? Tell me what the first one is.
Log, and then from 2 to 1.
Oh, so I jump right into it. Okay, before I jump right into it, let me do a little illustration on the board, then jump back into it. Guys, let me write a few expressions on the board involving exponents. That's what you're going to associate this word log with. And I say it looks like this. We'll start out with something basic. 3 raised to the zeros equal to 1. Everyone in class would agree with that. 4 squared is 16. No problem. 1/2 raised to the 3rd cube is 1/8. No problem. Let's try it right here. 8 raised to the 1/3 is, what's 8 raised to the 1/3? And what does it mean? 2. Yeah, 2. It says cube root of 8. So this means this, and Yes, the answer is 2, and I'll come back to all these. I was gonna try 16 raised to a negative 1/2. You stick a base.
-4.
I know why you said -4. Something else. I think I heard something else. I heard radical 2 over 2, something else. 16 raised to a negative 1/2. Does anyone remember what the negative sign means to do in terms of
Yes,
trying to
this is
come up with?
1/4.
We're going to do a reciprocal, we're going to flip it over. That's the negative sign taken care of. Then you're left with 1/2. And what does that 1/2 translate into you doing? Take the square root of this. You guys, what I do, this is what, 1/4? There's the answer for 16 raised to a negative 1/2. Just some exponents thrown in and just ask you to recall from background of what to do with these exponents. Okay, I threw in 0, 2, I threw a 3, I threw in a negative number, 1/3. Let's see, what else could I throw in for an exponent that might make it interesting? Why not? Let's try this one. 32 raised to the 2/5. I'd like to have an answer. Does anyone recall what raised to the 2/5 means? To do, not times 2/5, raised to the 2/5. Exponential, what does it mean? Anyone? Oops, we forgot. The 5 means to do this. This right here. Take the 5th root.
It's 2.
And then you take 5th root of what? 32. And then guess what the 2 says do afterwards? Square it. That's a translation of 2/5. Thank goodness I gave you a number that has a perfect 5th root. What's the 5th root of 32? 2. So this now translates into this 2 squared, and here's the answer. June? Mr. Park, can you think of anything else that maybe I should place here before I jump into my work here? Any other examples of a base being raised to an exponent, which is an exponential tonight? Can you think of another good example besides the ones I have? Or is that enough?
I think it's
That might be
good.
enough?
Yeah.
Okay. Now, you said, Ramsey, what are you gonna do with this? I could do that back in middle school. I'm gonna go back and rewrite each one of these on the side here using the word logarithm or log. Down here. Now, so please associate with logarithm exponent. And we'll rewrite, he's saying the same thing, a little bit more sophisticated looking. The log, on my first example, logarithm, the log, if I think of log as exponent, the exponent in this case is 0. I'm just looking at the exponent, that's the log. The log is 0. Notice I left a little space there. The log of what though is 0? The log of, when you use base 3, right, that's a subscript, of 1. So this and this in the black are saying the same thing, written a little differently. The next one says 4 squared is equal to 16. We know that. How's it look in log form? The log, or exponent, we get the exponent out of the way, is 2. Log of what is 2? Base was 4. That's my subscript of 16. Who would think? You're saying the same thing. Guys, let me write these down here right quickly. Log of, or log of, the exponent is 3 here. Base was 1/2. And of course I have 1/8. Next one, if I wish to write that in log form, in log, I'll leave a little space here. My exponent was 1/3. Base was 8. Where was this? 8 raised to 1/3 of this. Where was it? Is that true, guys, so far? Yes or no? Yes, yes. Now, what's my base here? Is the base 8?
Yes.
Now, what's left? I heard 2. It's right here. Next one, log. See all this on top of the board here. Log indicates the base is 16. In fact, we got 1/4 for an answer. No. Maybe 1/2. There's my exponent. Top of the board here. Base was 16. And I think we had a 1/4. The truth? Woo! Last one, log. And again, the log is associated with exponent. My last one, the exponent, I guess, was 2/5. My base was 32 of all bases, 32 here. And I think it was a 4 here. Just rewriting something that you've known all along, but use the word log. Rewrite it. Now, that rewritten, did I finally give a definition for what a log is with some restrictions here? With all that said, Marina, on that handout, what did I give for the definition?
Y equals logarithm base A of x.
Hang on, that's log base A of x means, hang on. What?
If and only if x equals a in y power.
A raised to the y.
A is more than 0.
Hang on, restrictions, A must be positive.
A is not equal to 1.
Don't let A be 1.
And domain of y equals logarithm base A of x is x more than 0.
Hold on, x must be greater than 0.
If the base A is the number e, y equals logarithm base e.
Now, get that way. Guys, she's telling me, Professor, after all that work over there, here's my definition. Log base A of x means what? And when you look at the mean here, it's doing much what we were doing with the numbers over here. We're doing basically the same thing, except now they give me a nice definition. And they threw in that definition, A raised to the y is equal to x. They're saying, yes, make the base positive. Don't let A be 1. And the domain, the x here must be greater than 0. And that's the way it looks. Wow. Now, Rena, what did I have after that definition?
If the base A is the number e,
Yes.
y equals logarithm base e of x equals logarithm of base 10 of x.
Now you're saying, Professor, let's bring that e in. Let's have that base A up there to be e. And all the restriction for A was it's got to be greater than 0. Well, Mr. Park helped me out. E is greater than 0. It's 2.718. So I can use it as a base. And when I do, though, it comes up so much in mathematics, they abbreviate this a little differently. If I use the base e, they abbreviate this as not log, but ln of x. Not log, they change it to ln. Only if the base is e. That special number we looked at, 2.718. Okay, they call this a natural log in mathematics. ln of x. Irina, we're going to finish this up here shortly. What types of questions did I have there, or did I have any, to look at with this?
Yeah.
What's the first one?
Number 1, logarithm base 2 of 1.
Okay, log base 2 of 1. Right? Answer immediately is 0. And I'll put a comma here. Why? Because 2 raised to the 0 is equal to 1. The answer though is 0. What's the next one?
Logarithm of base 7 of 49.
Hang on. 7 of 49. Guys, we know that's 2, comma, y. Base 7 squared is 49. I'm just looking at the exponent there. What's the next one?
Logarithm of base 3 of
Wait.
1 divided
That one has to be,
1/2.
I got you on that one.
Minus
Minus.
Is it -2?
Yeah.
And the reason why is 3 raised to a -2 is 1/9. These are the answers, guys. I'm sure you have justifications for the in there. Rita, what's the next one?
Logarithm of base 1/3
Oh, base 1/3, okay.
of 27.
27, be careful. Is,
-9.
say again.
-9.
Oh,
Negative.
Minus.
we're negative, not 9.
-3.
Is it 83? Let's see if it is. We'll check it. 1/3 base she gave me. If that answer is -3, this should check. Raised to a -3, you hope to get 27. You guys will go a little further on this one. Yeah, 1/3 raised to a -3 means 3 cubed. And yes, it checks. What's the next one?
Logarithm of base 32 of 8.
Log base 32 of 8. That's a strange one here. Boy, if it ever. I don't know whether the student could tell me right now what the answer is. Oh, I heard. Who said it? Susan. Okay, let's see what Joseph said. He says it's 2/5, Professor, right quickly. If you don't see it, guys, when they get tougher, you can say, wait, Professor, could I slow down and say, you're asking for this? You're asking for when is 32 raised to what power, exponent, is 8. You could do it on your own here. And then he's got the answer already, and what you could do and be clever, you could say, could I rewrite this as 2 to the 5th, that's 32, raised to the x, and this one as 2 cubed. Yes or no? And then common sense tells me, with those base 2's showing up, that this must be equal to this. 5x, the exponent, must be equal to this exponent. And I think, Joseph, did you say 3/5? There's the answer. So guys, to run the one that's a little bit tougher, go ahead on the side there and rewrite it. Do a common base, and then just work it out. What's that, the last one?
No, there's
One more, what's that?
ln.
Oh, ln, base e, hang on now. Those they will not write base e for you, but they use ln notation, it's implied as base e. ln what?
Root square
Square root e? Does anyone have an idea what that is?
1/2.
I hear it. Now, let's put a justification here. Understood, not written. I'll put it right here just for the sake of what we're doing here. Understood being E for the base. If they use that LN notation, natural log. He's telling me E raised to the 1/2, Professor, is the same as square root E. And I agree. Good check. It is 1/2. Wow, have we done some work today? I am telling you, we're not quite finished. I haven't even turned the exams yet. Jeez. I said, Ramsey, could we take a breath? I said, Sebastian, I'll take a breath. Move on. Okay, now, Arena, you've been helpful. Is there anything else there in that particular part?
Yes. In this part, no, there's no.
Oh, then we move to section what?
Same section, just in other than
Okay, so I may get very close to closing down the measure test back to you. First, guys, let me step back. If I were a student on a Monday session after a weekend and come in and professors talking about inverses, composites, what else did we talk about? Inverses, composites, exponentials, logarithms, and all these things to follow and be careful with. I said, whoa. This chapter 4 could be overwhelming. But, here we go. She's telling me, Professor, there's something else on that handout. But, Irina, before I do it, before we close down, got all this down, guys, I'm proud of you. I guarantee you, as we get through all this, the next part of the course will be easy. The trig is gonna be nice for you when we finally get there. This can be demanding. I want to do something before I jump in and finish up. I'm gonna go back and grab 2 raised to x for a reason. If I graphed it, I did a table, I want to see it for a reason. You guys remind me, not make a mistake. I think the y, was the y-intercept 1? I think it was. And did the graph look something like this? Yes or no? That was y is equal to 2 raised to the x we saw earlier. We'll connect something, make my lessons. Now I'd like to graph on the same grid. Try red. This. Got that in red. Log base 2x. Now let's see what we're doing. We'll see what that graph looks like. I would suggest, this is me, you could rewrite this quickly with the discussion we had today as that.
Yes.
That could be rewritten like that, based on what we did up there. Then I could do a table here. Since I did a table for 2 raised to the x at the beginning of class, let me, as we end class, well, I'm not going to call these concepts, just quickly form a table to satisfy this. That's what that means. Now, since I got 2 raised to the y is equal to x, I think it'd be wise to put my numbers this time at random in the y column. Because I've got to take 2 raised to the y. So in the y, just a mix of numbers. We'll try these. And then on the side here, this x should be 2 raised to the negative 2. We'll come back to it. 2 raised to a negative 1. 2 raised to the 0. 2 raised to the 1. And finally 2 squared. Which I think this one's 1/4. This one's 1/2. We squeeze those in, guys. 1. This is 2. And this one that we'll squeeze it in is 4. You guys see that? Okay. Then we'll plot those in the red, on the same grid. In the red, I start out with, go out 1/4 and drop down 2. Let me make sure there's a space for me. Let's see what I need here. I do not. -1, -2, down here. I think this was reasonable if we're closing down here. And that's the y, the x goes out to a 4. Right there. Now let's plot these in the red. First says move out 1/4 and drop down 2. Guys, out 1/4 down 2. Well, let's say right in there. Next says move out 1/2. Move out a little bit further, but drop down 1. A little further down 1, and say it's right there. Next should be 1, or was it 1, 0? Yes, make this look reasonable. 1, 0, that's here. Next is, what was it, 1, 0, I'm looking at it, was it 2, up 2, I think, was it, or 2, was it 2, 2? Was it, guys, was it right here? Was it, or not? Did we put that in there wrong, was it 2 to the first? I think I used a 1 there, didn't I? It was a 2, was it 2, 2, or not? Help me out, or am I down here at this one? We got this one out of the way, we got this one, if you guys agree. And then I put a 2 in there, oh, we got 4, didn't we?
Yes.
Okay, so that means what, out 4, up 2? Okay, out 4, up 2, please tell me out 4, up 2. Now, did we get that right, because I'm on top of the 4 here, what's wrong here? Oh, out 4, up 2, yes, it's supposed to be there. Let's go out 4, up 2, we mark 2. And Please tell me as I do it, am I somewhere in here? Let me down a little bit lower. Yes or no? Whew. Based on the table. Plot those in the red, just based on the table. Does that graph look something like this? The red graph. And the red graph is supposed to represent this. We did it through a table, log base 2x. The black graph from earlier today was this graph. Does anyone see any relationship between those two? That's not quite a good way to close down. You got the one I started out with. I started out with 2 raised to the x before the break. That's the black one. Now we went through a little table in the red there and got a red one, that's the log. So what's going on?
They're inverses,
Why are they inverses?
because they flip over y equals x.
If I plot, draw in y equal to x, you say, Professor, if you draw this line, even I'm doing it free-handed here, y is equal to x, is one graph reflected across the other, that y is equal to x? Is there a reflection across that y is equal to x to go from one graph to the other? And I'm sitting back and looking at myself, guys, you think so? So I reflect one graph across that line to get the other graph. So these two are reflections of one another. He says, Professor, not only that, they're inverses of one another. What a good way your professor set this up for you. I started out with inverses before the break, now we end with inverses. Those two are inverses of one another. Is it true? Now, if they are, Philip, you help me out here. Tell the class what would look like a check if I say the black graph function and the red function, they are inverses of one another, and you're trying to check it. What would that look like as a check? And I'll show you what I'm looking for. Could you show me what this may look like? It's going to be interesting. And it's supposed to be equal to x. That's where you check a function and its inverse. We can talk about that. What would that look like on this? Here's an idea. I'll write like this, f of the inverse. I'm going to close down this. You guys worked hard enough today. Yes?
Would it be 2 to the power of log 2x?
Okay, I want the inverse placed into the original function. But guys, I'm gonna call, this is my original function. That's from this morning. Is that true, guys? That's my original function, 2 raised to the x. Now, I want that inverse, which is this, brought in there. So what would that look like? What would that look like if my function's here and its inverse is there? And you're doing a composite on it. What would that look like? 2 raised to 1. It's been a long day. Joseph? Or 2 raised to what? Staring at you. Go.
2 raised to the x.
Nope. Not for what you see, not what I want here on the grid. Oh, it looks strange. I think you shouldn't see it, but there's, I'm not going to say it because it looks too strange. 2 raised to what? Okay, read it to me again. Log base 2 x. Look at how strange it looks. And that should be equivalent to, for a check, x. That's what we talked about earlier. Check it. Placing one into the other. And I know it looks very strange, and right there it is. And before we do close down all that business, guys, look at this. 2 raised to log base 2 of x is x. Let me ask you this. Suppose when you finally see this on a quiz or an exam later on, you saw this. 3 raised to log base 3 of, let's say, 7, what could you quickly, based on what you see in here, automatically, it's 7. Based on this. Who would think? Just walk up to you in the hallway and ask you, 3 raised to the log of 7 base 3. Professor, you're talking about 7. Now, in general, and close down, a raised to log base a of x is x. I think that's a good place there to stop because I sort of started with this. Wow. I see by the looks like, whoa, Professor, this chapter 4 is loaded with information. And I don't think we're quite finished, are we? And no, I don't want to do anything else because I got to turn tests and talk to you guys a little bit. There's a little bit more there, right? So that little bit more can be done. And hopefully I can jump into, maybe tomorrow, start chapter 5. Now guys, just clear your mind, think about it. Anything to ask about though? Mike, as we start